Hello, my name is Binay Tripathi,
My name is Victor Nazlakanyan.
and today we will be presenting our recent research in attempting to predict pivotal mRNAs as biomarkers for early detection of ovarian cancer. And in the next slide, I'll talk about what the motivation is behind trying to identify those significant microRNAs. It has been studied that the leading cause for the death of women all across the world is ovarian cancer, and the reason for that is the diagnostic processes that are currently available in the market are invasive and sometimes often increase the chance of these cancers after the test, and often the ovarian cancer is diagnosed late in the stage of cancer life cycle. In the next slide, I'll talk about what the researchers have turned to in the search for their answer. And microRNAs are some of the is one of the thing that the researchers are closely looking into. You know, these are short 20 to 25 nucleotides long RNAs that are extremely important in regulating gene expression. Now, in the next slide, I'll talk about the structure of the dataset that we use to analyze um, our findings. And thanks to Tian Zhou for making this beautiful visualization that shed some light on the type of data that we're working with. We worked with 21 separate experiments that were similar in nature, but each had their own multiple classes of cancers that they worked with. And now I'll pass to Victor for the rest of the report.
Thank you, Binay. So, what we saw here when we started the exploratory data analysis is first we noted there were no missing values, so no imputations were necessary. And we noted that of the close to 1,000 columns, they were pretty much all numeric except for the problem ID, as Binay mentioned, with different subproblems. When we looked at the distribution of problems, we saw that problem 4, problem 6, some of the problems were unbalanced. So we applied SMOTE upsampling to the problems. For the binary classification task, we basically applied SMOTE to be, for the minority class, to be about 50% of the majority class. And then we did equal resampling for the multi-class problems. And you can see here what the distribution turned into. When we did our feature engineering, we started with a basic standardization of the data set. Then we opted to do principal component analysis, and we opted to do this because of the nature of how many columns there were. There were almost 1,000, so we definitely wanted to reduce the dimension because of the cursive dimensionality. When we looked at the plot comparing the number of components against the explained variance, we were looking for an elbow in the plot that would signify what number of components led to a decrease, only a minor decrease in explained variance for each subsequent each subsequent increasing component. Unfortunately, this plot was pretty smooth. It was a very nice like logarithmic scale here, so we didn't really have a good number to pick. So we actually just went with like a heuristic of about 80 to 85% of explained variance, which was about 500 components. So that is about half of the columns. Then we did some Bayesian target encoding for the mathematical models, and what this is essentially in addition to target encoding, this calculates some of the higher posterior distribution moments. So like mean and variance in addition to the target encoding. This will help the prediction. Here's our neural network. So our neural network here, the architecture we went with is 3 hidden layers of 24 perceptrons each, an input layer corresponding to each principal component, and then an output layer here with each class. For each layer, we had batch normalization, dropout layers, and ReLU. In order to do some of this regularization, we went with 35 to 45% dropout probability after a really extensive hyperparameter search. For our ensemble models, we had these 4 models, and after a extensive randomized cross-validation hyperparameter search, we saw that XGBoost outperformed the other ensemble models with the final hyperparameters as such here. So our experimental results indicated that the neural networks overfit the data very easily, even with a ton of regularization such as weight decay and dropout. But the XGBoost performed a lot better. So really for these small data sets, it's better to perform cross-validation and not use neural networks. Thank you so much for watching.
Thank you so much.